Welcome back. Today we're going to talk about functions and their properties. And this is the beginning part of chapter 1. And so this is going to form the basis of our understanding for what we're talking about when we start to look at graphs and when we start to figure out what can possibly go into a domain. Why does the graph look like the way that it does? And so let's look at the relationship between function, domain, and range. So when we're looking at function, domain, and range, the thing you have to remember is that functions are really kind of like, in a lot of ways, they're like a machine, okay? And so when we think about a machine and what it does, we've got something that goes in, and that's going to be the domain. So the domain goes into the function, and inside of here, and so typically this is our x. So f of x equals y. So when we do this function to x, we get y. And so the thing you need to remember is what comes out is y. Okay, so this is the range. I know you know this. The domain goes in, that's the x values. Inside something happens to it and it becomes y on the other side. Well, the thing that we need to remember is with domain and range that if it's going to be a function, it has to do the same thing every time, and it can't do a couple of different things. So it means like this. If I put an x in, x1, I'm going to get out y1. If I put an x2, I get a y2. I get an x3, I get a y3. I get an x4, I can get y3. Okay, and so everything needs to map to one single thing. Okay, so that's a function. So every x maps to one y. Okay? The problem becomes if I ever have a situation like this where x1 could become y1 or x1 could become y3 and then x2 becomes y2, x3 becomes y3, and x4 becomes y4. X's map to more than one. Why is this a problem? Well, think about it like this. If you've got a machine and you're supposed to put in, the plastic and it's supposed to spit out, a Barbie or whatever, and you put in the plastic and the first time it spits out a Barbie and the second time you put in the plastic and it spits out a Ninja Turtle, that's a problem. The machine is broken. Okay, the machine is broken. Now, you could put in some green plastic and it spits out a green Barbie. You could put in some blue plastic and it spits out a blue Barbie. So that's kind of like it's still doing the same thing. That would be like more than one X mapping to a Y. So, no matter what you put in, a Barbie still comes out. But if the machine is broken, then you don't know what. You put in the same thing and you don't know what's going to come out the other side. That's when it's broken. And so what does this mean? It's kind of easier to see this graphically. Of the three graphs shown, which is not the graph of a function? And so imagine this. I put in an x equals -1, I get out -0.5. I put in x equals 1, I get out, let's say, a 0.5. This one works. For every x, it maps to one y. Okay, boom, 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 boom. Go down the line, down the line, down the line. It's fine. Okay? This 1 here maps to this point. If I go straight across, this is a second x. So let's call this x1. And let's call this x2. Well, x1 and x2 map to the same y value, which is fine. I put it in, I get that out. This one, same way. I've got these peaks. So this x1 maps here, this x2 maps there. It's fine, it's still a function. I put in an x, I get out a y. But look at the difference here. When I put in x equals 1, then y could equal, let's see, y could equal about, 2.1, or y could equal, gosh, this is a tough one, -0.5, or y could equal -2. And so you put in this x and you don't know what comes out. The easiest way to see this is to do the vertical line test. Check it out. Every x, so every x touches only one y. Every x touches only one y. These x's, so vertical line test, should not cross graph more than once. Okay, so for the vertical line test to work, it shouldn't cross the graph more than once. So this one is good. This one is good. This one is no good because our vertical line crosses it more than once. Okay, that tells you that at a given x, I've got 1, 2, 3 y. That can't happen. Can't have more than one output for the same x. Okay, and so what does that mean? Check it out. For these two, every x maps to a y. Some x's graph to the same y, which is fine. For this one, I've got 1x and it graphs to 1, 2, 3 y's. That can't happen. This is no good, no bueno. Vertical line test. So immediately, you draw a vertical line or you put your pencil on the paper. Does it touch more than once? Not a function. So what does this look like domain-wise? Let's find the domain of the function. If I'm looking at domain of a function, I'm asking what will work? Meaning give real values for y. Okay, so I put in this domain, whatever it is. It's got to spit out a y value that's real, that shows up on the graph. And so another way to think about this is what will break it? Meaning give imaginary values or undefined. Okay, so if you find something that's supposedly in the domain that gives imaginary value, a complex value, or it makes the function undefined, meaning like a divide by 0 or something like that, then that's not in the domain, so we have to eliminate that. So let's just check out the way that this looks. Okay, so what I'm looking for with a square root, this can't be negative. Okay, so like negative 36, that's an imaginary value. So the real domain, it can't be negative. And so what I have to say is that just the inside part has to be greater than or equal to 0. Okay, it's got to be greater than or equal to 0 because I can't have a negative under the square root. This is something that's going to come up a lot. Okay, so anything under the square root has to be greater than 0. Okay, and so if I subtract 2, x has got to be greater than or equal to negative 2. Okay, so my domain should be expressed as an interval. Okay, that's why we've been practicing writing things as intervals so often. So my domain expressed as an interval is negative 2 to infinity. Okay, so that's my domain for this one because underneath that square root it cannot be negative. Okay, so let's look at a second example. Second example will look like this. So this is essentially A. Let's call this B. G of x, and this is how we're defining our functions, g of x, f of x, h of x, whatever, square root of x over x minus 5, okay? So let's look at the things that could possibly go wrong here, okay? What's going to break it? Well, on top, this has to be greater than or equal to 0. On the bottom, what can't I put on the bottom of a fraction? Well, on the bottom of a fraction, this can't be 0, so this can't equal 0. And so I have to rectify those two things. So for the top, if x has got to be greater than or equal to 0, and on the bottom, x can't equal 0, when I put those two things together, this is the part where students get confused sometimes. When you have a top and a bottom, and the functions are different, obviously these are, if it says it's got to be greater than or equal to 0, and it can't be equal to 0, you have to combine those two things. And so think about it like this. So this is 0 to infinity, okay? Well, on the bottom here, this part can't be equal to 0. So this really means x minus 5 can't equal 0. So x can't equal 5. So think about this for a second. If I just consider the top, it's 0 to infinity. If I consider the bottom, this is my domain, negative infinity, all the way up to 5, not included, also 5 to infinity. Okay, so check that out. And so, how do I put those two things together? Well, this part limits everything below. This part takes out just 5. And so really, to put those two together means this. It goes from 0 to 5, and also from 5 to infinity. Does that make sense? Okay, so if I've got my numbers from 0 to infinity, so let's just draw a number line. So if this is 0, the graph of my top one would be like this. The graph of my bottom one would look like this. So from negative infinity all the way up to 5. So 5 is not included, so it's going to look like this. And I've got to have the part that has both colors. So it's this from 0 to 5 and from 5 to infinity. Does that make sense? So if you ever get confused and you're like, I don't really know, draw a number line. And it's the part of the domain that works for everything. Okay, so if it doesn't work for one of the parts, it can't work at all. All right, that's finding domain. Let's find the range. I want to sketch a little graph of this. And when you plug this into your graphing calculator, you're going to get something that looks this way here. Draw it in red here. Yeah, I'm doing graphing noises right now. Graphing sound effects. All right, so you've got kind of this like, you know, inverse function graph. And so the range is the y values. So to think about y values would be like, where does the graph touch? Okay, so it touches all this, but what doesn't it touch? So y can't equal 0, right? So there's this asymptote at 0 right here, right? We're going to talk about asymptotes in just a minute. So this is asymptote at 0. So my range, all real numbers, except 0. Okay, so all real numbers except 0. So what we're going to do is sometimes a graph can be kind of deceptive. So we've got this guess that that's can't equal 0. So here's what I'm going to do. I'm going to say we're going to actually see, can y equal 0? Can 0 equal 2 over x? Well, no, because if I multiply by x on both sides, I'd have 0 equals 2. Well, this doesn't work, okay? Does not work. And so I'm not going to, that looks like an X, so I'm just going to cross it out. This does not work. It's confusing because I can't have a 0 on the bottom, and you know that. Okay, you know that. So if we look at it from an algebraic perspective, literally y cannot equal 0. There's nothing I can put in for x to get it equal to 0. I solved it right here. There's nothing I can put in. But we need to look and see, well, what if I can't see it? So what if there's a part of the graph I can't see? And so we're going to test all numbers. Okay, so here we go. We're going to say k is some number. So k equals 2 over x. Okay, so this is non-zero. So we're just saying, what if k was 1,000,000? Could I get my graph to equal 1,000,000? What if k was 1.6? Could it equal that? So I'm just going to generalize it and say k is equal to 2 over x. And so I've got 2 is equal to kx. Okay, so x is equal to 2 over k. What is the only thing that k can't equal? Okay, k could be anything. Okay, so k can't equal 0. What that tells me is that is the only thing that does not work. Okay, that's the only thing that does not work. All right, and so what is my range? My range is negative infinity all the way up to 0. 0 is not included, and it's 0 to infinity. That's my range, written in interval notation. Continuity. Here's the easiest way to think about continuity. Can I draw the graph without picking up pencil. Okay, can I draw the graph without picking up my pencil? So check this out. Look at this blue curve here. If I was going to go and draw this, I'd go graphing noises. Well, if it came from up here, we go. This is where graphing noises are important. And so what we'd say about this one is this is continuous at all x, because I can draw the whole graph without picking up my pencil. Okay, this next one, I'm going to go to draw it. Make the noise. Do it while you draw it. Oh, see that? That part of the graph is up here. I know that's kind of confusing. You've probably never seen that before. But this is discontinuous. Okay, discontinuous means I'm drawing my graph and I have to either pick up my pencil or I draw part of it and draw another part. So in this case, there's a hole right here. And we've removed that function. So the f of a, so whatever a value that is, we've removed it. And so this is called a removable discontinuity. That's a removable discontinuity. Down here, again, watch. Removable discontinuity. Okay, so that's a removable discontinuity. Okay, this one. This is called a jump discontinuity. Okay, because my graph literally is going and then it jumps up or jumps down. Okay, this one. See how it drops off into infinity there and it comes from infinity? This is called an infinite discontinuity. An infinite discontinuity has this situation where an asymptote takes my graph to infinity, but I can't keep drawing. Okay, so it goes down and then I got to pick it up and I got to start at the top. So can I draw it without picking up my pencil? Okay, so if we're going to identify points of discontinuity, literally what we're saying is where's the spot that it's not defined. So this one, watch, this one's continuous. I just draw it. This one. So, which of the following figures shows function that is discontinuous? This is a hole. Okay? Discontinuity. It's removable. So here's an opportunity for you. Draw a graph that's discontinuous at x equals 2. Try it. Pause right here. Try this. And then when you come back, we're going to draw one together. All right, we're after the pause. Here we go. There's tons of different ways to do this. But I'm going to go like this. So let's see. X equals 1, x equals 2. I'm just going to put a hole right there. What do I have to do up to that point? Nobody knows. There it is. Removable discontinuity. You could also do a jump discontinuity. You could also do an infinite discontinuity. Bunch of different ways to do it. Increasing and decreasing. Okay, increasing and decreasing functions talk about the general trend of the data. General trend of the data. Is it going up? Is it going down? Is it doing neither? Okay, so this one is increasing. We say increasing on x. So for the whole domain, it's increasing. It's going up to the right. Okay, up and to the right. This one is decreasing on x. It's going down and to the right. This one is a straight line across. There's no life to this data. This is constant. on x. Okay, so it's going straight to the right. This last one is a little bit tricky because notice, down, across, up. So the general trend is three different things. It's increasing. Well, let's start with decreasing. It's decreasing from negative infinity all the way up until, now we're defining this by its x, because we're talking about on the domain, right? Increasing on x, constant on x. So this is decreasing from x equals negative infinity to negative 2. And that is included. It is constant from negative 2 all the way to 2. It is increasing from 2 to infinity. Okay, so this part is going down. This part is going across. This part is going up. Okay, increasing, decreasing, constant. Okay, this one. Okay, this is just an actual graph. Okay, these other ones are actual graphs, but this you can see the points. Okay, and so if we are talking about what it actually means, my change in y over my change in x is negative. Okay, for this part. So my change in y over my change in x is going down. My change in y over my change in x, it's 0, but it's got to be over a positive number. Okay, so my change in x has to be positive. This one, my change in y over my change in x is positive. Okay, negative slope, no slope, positive slope. Okay, and you include it in those intervals here. Okay, so this is from negative infinity all the way up to negative 4. This is from 4 to 2. And this is from 2 all the way to infinity. Okay? That's how this works. Defining those intervals of increasing, decreasing, and constant. Okay? Here's a piecewise function. So look, just check out what's going on here. You're like, oh my gosh, I don't know what's going on. This is a piecewise function, so it's defined by 3 different parts. Okay, so check this out. Here's our function, x plus 3, f of x plus 3 minus, or sorry, absolute value of x plus 3 minus the absolute value of x minus 2. So it's equal to, meaning this is what our function actually is. It's negative 5 if x is less than or equal to 3, negative 3. It's 2x plus 1 if negative 3 is less than x is less than 2. And 5 if x is greater than 2, greater than or equal to 2. Raise your hand if you have no idea what's going on right now. You're not alone. I'm going to help you out. So here's what this looks like. They just told you what the pieces of the graph look like. Okay, so check this out. This over here is the domain. And this is f of x. Okay, so check this out. On my domain, x is less than negative 3. So here we go. Here's negative 1, 2, 3. Okay, so all the way up until this point, x is equal to negative 5. So my graph, f of x, literally is negative 5. So it's a flat line all the way up until x. So x is less than or equal to negative 3. Right there. Okay? From negative 3 to 2, so all the way from, so this middle part here, it's 2x plus 1, so up 2 over 1, up 2 over 1. So it's going to end up like this. So it's 2x plus 1 literally on that interval between those two things. Okay? And x is equal to 5. I'm sorry, I messed that up. I drew my graph wrong. Should be up 2 over 1. Up 2 over 1, up 2 over 1. So this is going to go all the way to 5. Super straight line. And then it's 5 when x is greater than or equal to 2. So here we go. So literally, the graph is defined by these functions here. It's negative 5 all the way up until x is equal to -3. It's 2x plus 1 between -3 and 2, and it's 5 from 2 on. And so here's my increasing. So here's increasing, and these two are constant. So increasing from -3 to 2. Are they included? Let's see. Well, what does this tell you? They're not included. It's constant from -infinity all the way to -3, included, but also from 2 to infinity. Okay? Piecewise function, guys. It tells you exactly the intervals where it's increasing and decreasing. Okay? All right, let's keep rolling. Another principle in this one that we're going to talk about is lower bound, upper bound, and bounded. Okay? So, boundedness has to do with having a value. I'm going to scroll down here. Lower bound, upper bound, bounded. So lower bound. A value of y that is less than all others in the graph. Of f of x equals y. Okay? An upper bound is a value of y that is greater than all others in f of x equals y. And bounded means it has a lower and upper bound. So you're probably like, I don't really understand what that means. Well, check it out. Look at this. I've got this graph here. Okay, whatever it happens to be. If it has a lower bound, I can literally draw a line below the entirety of the graph, meaning every value is above it. Okay? Yes, this has a lower bound. So I can draw a value below it and the graph doesn't cross it. If it has an upper bound, I can draw a line and nothing touches it. So there's a value at which the graph doesn't cross it. So it's kind of like it bounces between these two values. This one does. So this is an upper bound. So this one is bounded. It has to be. There's two values, doesn't matter what they are, two values which it's between them. This one here, check it out. Does it have a lower boundary? No, because there's no value I could draw that's low enough that the graph doesn't cross it. However, there is an upper bound. Assuming that it doesn't do anything on the sides here. We're assuming that this is the full picture of the graph. It's got an upper bound because I can draw this boundary up here, and it doesn't go above it. This one here, it's got a lower bound. Okay, it's got a lower bound because there's a value that it doesn't go below. Everything is above that value. This one is unbounded. Because there's no value up here, it keeps going. There's no value down here, it keeps going. That's boundedness, okay? Local and absolute extrema, okay? Local and absolute extrema have to do with where are the bumps in the graph, okay? The highs and the lows. Okay? The highs and lows. For example, let me just draw you a little picture here. If I've got a graph that looks like this, where's my maximum? Here's my max right here. This is my max of my graph. Well, right here, that's a pretty cool point. It's kind of a little max in that local area, right? In this little area. So this is the max in a local area, right? I'm going to put in quotes. A local area, meaning it's a max, but it's not the absolute max. It's like You didn't climb Mount Everest, which is the absolute max. You climbed some other really tall mountain that was local in that area. And down here, here's another one. This is a local max. So think about it. You didn't climb the highest mountain in the world, because the highest mountain is the absolute max. So you didn't climb Mount Everest, but you climbed a really tall mountain that was in that area. So it's still impressive. So these local maxes are these other bumps in local areas, even though they're not the highest one on the graph. Okay? The mins work the same way. So if I've got a graph here that looks like this, okay? So I've got the ability to identify, this is my absolute min. This is a local min. I didn't go to Death Valley, but I went to a really low spot, right? Again, here and here, these are local mins. Okay? So these little bumps, these local mins, these local maxes are places where it's significant. It's low compared to the other values, like it's low here, but the absolute min is actually way down here. So check this out. Decide if it has any local maxima or minima. If so, find each local max and value, maximum value or minimum value, and the value at which each occurs. So this is going to be the case where this right here, this is the absolute max or absolute min. Okay, this is an extrema. Okay, they're called extremas because it's like extreme meaning extremely high or extremely low. Okay, so this is the absolute min seemingly, but on this location, this would be a local min in this area. Just so happens to be for the whole graph. How do we find this? Well, this is going to be where we use our calculator to go second calc, and we're going to use the min and max functions. Okay, so if I set my interval, you know, here with my calculator, so I set that left bound, I set that right bound, right, and I guess. This one here on my graph, so I plug this into my calculator. This one here is going to be at negative 2.05, comma, negative 24.06. Now you're going to have to adjust your window perhaps, but that's my answer. So if you go in and you try that, so practice that with your calculator, practice it, and then you'll find the absolute min, absolute max. Right here we're going to have to use the local, so this is the local max here. So use the max function. So again, define that interval. And this one, when you get done doing it, you're going to find that this is 0.46 and 1.52. This one here is a local min, and it is at 1.6 comma negative 1.77. Okay, so you're going to use the second calc. Minimum and maximum functions, and you're going to define your interval to give you just that piece. What's going to happen is if you do too wide of an interval, or you calculate the max or min, it's going to be wrong. So make sure if you're looking for a max, you use the max function and you define that max right there. Okay. One more topic: symmetry. Symmetry is, can I fold it in half? Okay, in this case. So symmetry to the y-axis is, can I fold it in half over the y-axis? So if I graph this here, I can fold it in half. Yes. So if this is xy, negative xy is on there. So over the y-axis. So I've got an x, I've got a negative x, and they graph, so the y value at x and negative x is the same. Okay, so this is also an even function. Okay, that's an even function because if I do f of 2, it equals 4, and f of negative 2 also equals 4. Okay, so an even function says f of negative x is equal to f of x. Okay, symmetry, y-axis symmetry. Okay. Symmetry with respect to the x-axis. So check this out. This one's going to be, can I fold it over? So it's going to look like this. You're going to be like, that's weird. Okay? This is not a function. Remember, it doesn't pass the vertical line test. So this is not a function. However, it is symmetric with respect to the y-axis. Okay, so xy, okay, it also has x negative y. Okay, so respect to the x-axis means I've got xy, but I also have the negative y value for that same x. So they graph to one another. Symmetry with respect to the origin. There's a couple of ways to think about this. Okay. If I've got a function here, and I'm going to try to draw this. Not bad at all. Okay. I've got a graph here. Symmetry with respect to the origin means can I rotate it around the origin? Okay. Or if I've got xy, then negative x, negative y is in there. Okay, so if the opposite, so first quadrant, third quadrant, second quadrant, fourth quadrant, this is an odd function because f of negative x is equal to negative f of x. Okay, so this is the one that's confusing for students. So if I take f of x, it's equal to y. And if I plug in negative x, so f of negative x is equal to negative y. Okay, so xy, so f of x is equal to y, f of negative x is negative y. So the opposite domain input yields the opposite range output. Okay, so an odd function can be rotated around. It's got that symmetry with respect to the origin. Okay, so when we check a function for symmetry, here's what we can do. We're going to call it odd, even, or neither. And what I can do is I can graph this. And if you know about functions, you know that this is a parabola that's been moved up 3. So 1, 2, 3. If you didn't know that, you will know it very soon because we're going to study that in the next section. But you can graph it on your calculator. And so it's x squared plus 3. So it's moved up 3. Well, obviously we see that, you know, I've got this symmetry here. I could fold it over. So it looks like it's an even function. But here's the test. Is f of negative x equal to f of x? Okay, so let's see. F of 2 is equal to 2 squared plus 3, which is equal to 7. And f of negative 2 is equal to negative 2 squared plus 3 is equal to 7. So f of x, whatever it was, it just happened to be 2, is equal to f of negative x. Okay, so in general, it would look like this. F of x equals x squared plus 3, and f of negative x, so this is me testing, I tested a value, and now I'm going to test in general, is equal to negative x squared plus 3, which is x squared plus 3. Okay, so if you ever get the case, if you're trying to figure out if it's even or odd, you have to look back to those rules. Is f of negative x equal to f of x? Okay. Horizontal and vertical asymptotes. This is our last topic. I know this is a very long video. This is a very long section, but it's got a lot of pieces to it. The best way to do this is to talk about the horizontal asymptotes, HAs. Okay, so horizontal asymptotes are going to be abbreviated like that. It's going to be Bobo, Betsy, and Bo2, meaning bigger exponent on bottom, then x equals 0 is asymptote. If the bottom equals top, meaning the exponents on x, then x equals constant, the ratio of the coefficients of lead terms. If it's BO2, it's bigger on top, meaning exponents, then horizontal asymptote is undefined, meaning there isn't one. So this would be horizontal asymptote equals 0, x equals constant, ratio of the coefficients of the lead terms. This one would be the horizontal asymptote is undefined. Let's look at a couple of examples. Well, okay, vertical asymptotes. Let's do that first. Vertical asymptotes. Where is x undefined? Okay, so those considerations would be like where are their square roots, where are their square roots, where are there a denominator, so is there something on the bottom that could make it 0 so that we'd have to exclude that x. So here we go. For A, f of x equals 3x over x squared plus 1. Okay, so let's look at the exponent. So this is 1, so the highest degree coefficient is 1 on top and 2 on the bottom. So bigger on bottom. So bigger on bottom. So my horizontal asymptote equals 0. Okay, that's how that works. So my bigger was on bottom, so my horizontal asymptote is 0. For B, 3x squared over x squared plus 1. So when I look at my exponents, I got 2 and I've got 2. So this is a Betsy situation. Bottom equals top, so it's a constant. So x equals a constant, which is equal to the ratio of the highest degree coefficient. So it's 3 over 1, because this is 3, 1. So x equals 3 is an asymptote. Done. On this one, C, 3x cubed over x squared plus 1. And so my 3 on top, 2 on bottom, so this is BO2. Bigger on top, it's undefined. So think about it like this. My top is getting really, really big, and my bottom is getting big kind of fast, but not as fast. And so no horizontal asymptote. Let's look back at these three real quick. Do they have any vertical asymptotes? Are there anything that's going to make it undefined? On top, so we check the numerator, there's no square roots, there's no radicals. But on bottom, we've got these functions. Is there anything where x squared plus 1 could equal 0? Well, that would be x squared equals -1, so x would be equal to the square root of -1. Well, think about it like this. If it's not real, it can't be an asymptote. Okay, so no vertical asymptotes. This one, no vertical asymptotes. This one, no vertical asymptotes. We're going to do one more example. In D, I'm going to have x squared plus 2 over x squared minus 1. All right, so let's look. Horizontal asymptotes, bubble, Betsy, BO2. X squared. So bottom equals top. So it's a ratio. So Betsy. So it would be x equals 1 over 1. So there's a horizontal asymptote at x equals 1. For my vertical asymptotes, what's going to break the domain? I don't have any radicals. That's the main thing we're looking for. And the bottom equals 0. So x squared minus 1 equals 0. So x squared is equal to 1. So x is equal to plus or minus the square root of 1. So this is, there's vertical asymptote at x equals plus or minus 1. Okay, so x can't be equal to -1 or 1. Okay, so I have two vertical asymptotes in this case. I've got two vertical asymptotes and one horizontal asymptote. Okay, that's Bobo, Betsy, and BO2. Let's do one more example. For this one, I've got this crazy situation on the bottom, but it's not all that crazy. I just need to redefine it. So sometimes the task of finding these asymptotes is going to be redefining exactly what's happening. Well, if I factor this on the bottom, okay, so I need multiply to -2, add a -1. So I'm going to have x minus 2, x plus 1. Factor, if possible, y. Because if I'm looking for things that are going to make the denominator 0, what's the easiest way to do that? It's factor. Okay, so my horizontal asymptotes. Bobo, Betsy, Bo2. Well, I've got bigger on bottom, right? Because I got an x squared on bottom. So that means that I have x equals y equals 0 as an asymptote. And for my vertical asymptotes, I have x minus 2 is 0, x plus 1 is 0. So x is equal to 2, and x is equal to -1, make it 0. So x can't be equal to, well, those are my asymptotes. X can't be equal to 2, x can't be equal to -1. So these are my vertical asymptotes. Okay? That's the deal, guys. That's how this works. So, an important note about asymptotes. With asymptotes, so even if it's going like this, if the graph approaches a value, into infinity, it's an asymptote. Okay, so for this one, like x equals 0 is an asymptote. Sorry, y equals 0 is an asymptote because this graph approaches it as it goes to infinity. Still makes it an asymptote. Even though it crosses it at first, it's approaching it as it gets into infinity. Okay? It's just what it's getting closer to as it goes to infinity. All right, guys? That was a super long video, but it's a huge section, so please, if you have any questions, contact me. But thanks for watching, and we'll see you next time.